Hey folks, welcome to the video. In this video we're going to be talking about the Schrödinger equation. In particular, we're going to derive the Schrödinger equation using operators. The history of mathematics has been a history of increasing abstraction. We start out with numbers that describe quantities of items around us. We relate these numbers using arithmetic. But then we start thinking, well, the number of items could change, they vary. So we start talking about variables. We relate variables using algebra. And then we start thinking, well, we could have quantities that depend on variables. We call these functions. We use calculus to relate functions. In particular, we use operators to map functions to other functions. This video will be a fantastic application of how abstracting from numbers to operators takes us from classical mechanics to quantum mechanics. I hope you enjoy.
In classical physics, we learned that energy, E, is equal to the kinetic energy plus the potential energy. Now, we can represent the kinetic energy as 1/2 mv squared, where m is mass and v is velocity. We can also rewrite this as p squared over 2m, where p is the momentum of a particle. The momentum we know is mass times velocity, so we can do a simple check to see if this is in fact the kinetic energy. That check can be done by substituting in p equals mv into this expression. So we get mv squared over 2m. Rewriting this, we get 1/2 m squared over m times v squared, which is 1/2 mv squared. And that's the kinetic energy. So this checks out. Now, the next step in this process is to talk about this energy equals kinetic energy plus potential energy in a different form. Right now, E equals k plus v is a number. Energy here is a number. In particular, it is a physical observable, something that can be measured. In quantum mechanics, we take physical observables and represent them by something called hermitian operators. So we represent physical observables by hermitian operators. So an operator, let's talk about that. An operator is an object, a mathematical object that takes a function, or really a space of functions, and maps that to another function. So, for example, the derivative with respect to time is an operator, the derivative with respect to position is an operator, and suppose we're given the function f of x is equal to x squared. So this is a function that takes in real values and maps it to real values. D by dx, the operator acting on this function, gives us 2x, and this itself is a function. So an operator is some object that takes a function and maps it to another function. Hermitian operators are operators that obey a very specific and special property. It's a property that allows them to have what are called real eigenvalues. For the purposes of this particular video, it's not so important that we understand what Hermitian operators are. What we do want to understand is how moving from numbers to operators, or representing numbers, these physical observables, by operators allows us to move from classical physics to quantum mechanics. So how do we do that? Well, the physical observables in E equals K plus V are E, the momentum P, and V. So this is an E equals K is P squared over 2M plus V. In this case, we want to turn each of these observables into some kind of operator. We know that V, the potential, is dependent on the system, so it is external. And so we represent V, the operator, just by V with a hat over it. Momentum, on the other hand, is what we call the generator of spatial translations. So an object moving in space carries with it a certain velocity, and so if you multiply that by its mass, it has a certain momentum. So momentum is the generator of these spatial translations. So we can represent the momentum operator as a generator of spatial translations using a derivative in space, a derivative in x, and multiplying it by some factor. In this case, we multiply it by negative I, where I is the square root of negative 1. And E, energy, on the other hand, is the generator of time translations. So just like momentum is the generator of spatial translations, E is the generator of time translations. So it would similarly be a derivative in time multiplied by some factor. In this case, the factor is positive I. Okay, so we have these three operators that represent the observables of energy, momentum, and potential energy. Now we can substitute these into E equals P squared over 2M plus V to get I d by dt, that's the E term, is equal to P squared gives us negative I d by dx squared over 2m plus v hat, where the hat just means it's an operator v. We can simplify this to get I d by dt equals this term here simplifies down to negative d squared by dx squared over 2m plus v hat. Simplifying even further, we get I d by dt is equal to negative 1 over 2m d squared dx squared plus v hat. Now, these are still operators, and these operators have to act on functions. They're going to act on a certain function. We write that function using the Greek letter psi, And this particular equation, for psi is a function, this particular equation is called the Schrödinger equation. It's one of the most important equations in quantum mechanics. And what just happened? We took physical observables in the energy equation and turned them into operators. When we turned them into operators, what we just did was move between classical physics and into quantum mechanics. So the increased level of abstraction we have given these quantities of energy, momentum, and potential have given us one of the most important equations known to physics.
Well, I hope you all found that interesting. Like, subscribe, and leave a comment down below. I'll be making more videos like this, so I'll see you guys next time.